Welcome back to Physics 142. I'm in the middle of doing more examples of magnetic induction and ways that we can induce current and induce electric potential in a wire by changing the magnetic flux. And changing the magnetic flux, we've been talking about that there are three different ways you can do that. You can change the magnetic field, you can change the area of your loop, or you can change the angle between the magnetic field and your loop. So in the last video, I did examples where we changed the magnetic field, and I did an example where we changed the angle. All right. Now I want to do one more example where we're changing the area, and in doing that, I want to introduce a concept which we call motional EMF. All right. And basically the idea of motional EMF, so we'll just write this down. All right. Motional EMF, all right, is basically that if you have a moving conductor, you can produce an EMF, all right? So this is an EMF, or remember EMF is basically the same as potential, right? EMF that you produce when a conductor moves, all right? And now, this doesn't just happen for any old conductor moving, right? If you have a conductor moving through a constant magnetic field that never changes, then, and you know, the conductor itself never changes and the angle never changes, then, you know, if nothing ever changes, then you're not going to induce anything. But if any of those are changing, then you will actually induce an EMF. And so I want to give just one sort of example of this. We've done a similar problem to this already in previous videos, but it's always good to do more examples here, all right? So let's do one example of motional EMF, and I'm going to draw a circuit here which has a bar on it that's free to move. All right, so you could imagine there's sort of a little contact here and a little contact here, all right, metal bar. And this metal bar I'm going to take and I can move it at some velocity v, all right? Now I want to give my circuit some dimensions. It's a square circuit. We'll say that this dimension is x, all right, is the distance sort of from here to wherever the bar is. All right, and we'll say that this circuit is L high, and maybe I want to put a resistor in the circuit. You know, I can do that, so I'll go ahead and I'll put a resistor in this circuit. We'll give it a resistance R, all right? And then I want to take and I want to apply a magnetic field, all right? So we'll apply a magnetic field, and I'll have my magnetic field go into the page, all right? So here's my magnetic field into the page. And, you know, the magnetic field extends quite a ways out here, we'll say, all right? So basically, as I move, I'm going to enclose more and more and more magnetic field. All right, so what you can see already is this is going to change the flux, right? And I should probably just draw in, you know, this is going to have some area, right? And so I'll just choose my area vector to be into the page here, all right? And if, you know, in these cases, I sort of have some choice, all right? But I'm going to choose my area vector to be aligned with the magnetic field, is sort of simplest here, so I'll have it be into the page. And so then the question is, all right, let's talk about the EMF that gets produced, all right? What sort of EMF gets produced in this wire, and what direction is the induced current? All right, so find the induced EMF, all right, and direction of I induced, all right? And actually, you know, we can also find the value for I induced. That also will be a good thing here for us to work out. So, all right, so how do we do it? Well, we've got to use, again, Faraday's law. So let's do it. EMF, all right, is minus d phi dt And in the case we look here, all right, the magnetic field is all uniform, all right, and everywhere over our entire area, no matter what that area is, you know, even if it's sometime later, all right, it's going to look the same, and the angle between them is always going to be the same. So if the integral over that area is always the same, then I can just write this as minus d dt of b times a times cosine of theta. All right. Now, in this case, what's changing? Well, the magnetic field is constant. I should give us a value for it, huh? So let's give the magnetic field a value b. All right. So the magnetic field is constant. All right. Theta, the angle between b, well, b is into the page and the area vector is into the page, so that angle is constant. All right. But in this case, it's the area that is changing, right? So we can write this as minus d dt of, oh wait, well, sorry, I'm going to pull things, we're trying to pull things out, right? We're pulling out minus b cosine theta dA dt, right? Now a is the thing that is changing. Okay, so good. Well, now can we write this in terms of the variables that were given in the problem? Well, what's the area here? The area here is going to be x times L, right? And as this gets bigger, then x is just going to get bigger and bigger, right? So I'm going to write this now. Well, in cosine theta, the angle between the area vector and the b vector is 0 degrees, right? So this is going to be cosine of 0, which is just 1. All right, so I can now write this as minus b times d dt of a is going to be x times L, right? Well, now I look at it. L is just constant, so that can come out, and so I can write this as minus b times L times dx dt, right? Because it's just x that's changing, and well, dx dt, that's my velocity v. So I could just write this as minus bl times v, okay? That's going to be my induced EMF. Of course, if I wanted that to be current, well, that's just going to be I times R. So if I want I induced, then I have minus BLV divided by R. So there you have it. All right, we've calculated the magnitude of the induced current, but what about the direction? Okay, what about the direction? Well, let's think about how this works. So, oh, excuse me, I apologize about that. We'll see if it has a friend coming. Not right now, okay. Well, let's see. The magnetic field is into the page. There's its pair. Okay, great. All right, so the magnetic field is into the page. Good. All right, and as we increase the area, that means the flux is going to increase, right? So we are, So we are increasing into the page, all right? So let's write that down. So we're increasing flux into the page, right? We're increasing into the page. So that means we want to induce a magnetic field that opposes that, right? So we're going to induce a B out of page, right? We want to induce a magnetic field that's coming out of the page, right? Because this is increasing into the page. So to induce a field that's out of the page, right? Well, to get a field out of the page, I would put my thumb up out of the page. I curl my fingers in the direction that the current would go. So a current that's going counterclockwise would make a field that's out of the page, right? So mark that on here, right? A current, an induced current that is counterclockwise, induced current will make a magnetic field that is out of the page, an induced magnetic field out of the page. Now, there's one other thing that I want to point out about this that I think is sort of interesting, is there's another way that you can think about the way that this induced EMF, this induced current, is opposing the change that created it. All right. Ultimately, the change that created this was I moved the bar to the right. Right. I moved it with some velocity to the right. Well, if we think about what's happening now, all right, we've induced a current that's flowing up in this wire, right? We've induced a current that's flowing up in this wire that I'm moving, right? So there's some current flowing up there, all right? And if we think about the force that this magnetic field then would, this current should experience a force from the magnetic field, right? We'd have, we can write that down, right? We have that force on the bar, right? The force on the bar would be this induced current in the bar times the length of the bar, right? Crossed with the magnetic field, right? Crossed with this red magnetic field here. And if we think about the direction that force would be, well, IL, that's up, right? And the magnetic field, that's into the page, right? That magnetic field was into the page. The red magnetic field is into the page. And so that's going to produce a force, right? A force that is back to the left that opposes the velocity, all right? So this force ultimately, right, this induced current, right, the force on that current will oppose the motion that originally created it. And so I think that's kind of cool. All right, we'll just make this opposes motion, right? We end up with a force, right? This will end up creating a force that opposes that motion, that change that created it in the first place. And so that is kind of cool. So, all right, there you have it. Hopefully those are some helpful examples of how we can calculate the induced EMF and the induced current from changing the flux going through some sort of circuit loop.